This is Module 8A. We'll be calculating the entropy change of liquids and solids and calculating the irreversibility of different processes. Entropy change of compressible substance such as a liquid or a solid. If you recall the fundamental property equation, du equals TdS minus PdV. If we take that a constant V, where the volume isn't changing, then ds equals du over t, or cv dt over t. So for incompressibles, we also know that cp equals cv equals c. And for example, delta S for liquid water from 25 to 35 degrees C would be the integral of c dt over t, or if we take it over a small range of temperature, that would be c, the integral of dt over t. So here we have delta S equals C times ln of T2 over T1, 4.18 ln of, well, you have to get it into Kelvin or absolute temperature and come up with an entropy change when it's heated from T1 to T2 of 0.138 kilojoules per kilogram K. Now let's take an example of an entropy balance on a heat exchanger. Suppose the liquid water is heated from 300 to 350 by 4 kilograms of hot air, entering at 400 K. Find out how much entropy is generated by the process. So first we'll do the energy balance. Mass of air, Cp, times 400 minus T out equals mass of water, Cp, times 350 minus 300. And solve for T out, it's 348.3 Kelvin. Next we'll do the entropy balance. Entropy generated is out minus in, so I'll take S generated. Here I have ln of T out over Tn for the air. It's coming out at 348 times its Cp plus mass of the water times ln of T out over Tn, both cases out over in. For the water, add those two together and we have a negative entropy change for the air, but a positive entropy change for the water, so it comes out, the whole thing comes out a net positive, and always has to be positive. So our irreversibility we'll call temperature of the surroundings times S generated. And let's think of irreversibility as the work that could have been obtained if the process had run reversibly while interacting with the environment at T0. So suppose that we could have generated some power rather than wasted that energy due to dissipation where entropy is created. So irreversibility is a measure of the inefficiency of a process in a scale that we can understand. So when we multiply it times T0, we get it into energy units, and here we have 25 kilowatts was generated in that process as irreversibility or dissipation. Meanwhile, we transferred a total of 209 kilowatts of heat. So while we transferred that amount of heat, 25.56 kilowatts of the opportunity to produce power was lost. Sometimes it's called lost work. Now suppose we used 4 kilograms per second at 500 K to heat the water, and recalculating we find that T out is 448, still drops by the same amount, but now I'm using higher temperature air to heat the water. Same amount of air but higher temperature, so now it's at a higher potential and it really has a higher quality. Don't need that high of air, but if we do, then we can make the heat transfer faster. But notice our entropy generated in that case was higher. Instead of generating, and our irreversibility was higher, calculate the irreversibility, comes out to 60.99 kilowatts. And we still transfer the same amount of heat. So when you use higher potentials than you need, when the gradient is higher, the irreversibility will be higher, and the potential to produce work, you've lost even more. So this irreversibility is now 60.99 kilowatts, whereas before it was, what, about 25. So I call this the driving force for heat transfer, the difference between the high temperature fluid and the low temperature fluid. Here the air is coming in at 500 relative to the water. There's a much higher driving force, and you'll see that you produce more irreversibility. Now in this heat exchanger we have a lower driving force, so it's a larger heat exchanger. We need a larger heat exchanger when we go with a small gradient, because we want to make the heat transfer. The higher the gradient, the faster the heat will transfer. So we can transfer it in a smaller exchanger when we use a higher gradient here on the right. So the point is, S generated is the function of the driving force, or a function of the gradients. Irreversibility of the process increases with the driving force used to carry out the process. So the speed of the process goes up, but the efficiency of the process goes down. So a process goes higher with high gradients. Here's an example. The heat transfer Q is equal to U, some heat transfer coefficient, times the surface area of the heat exchanger times delta T, the driving force. Now the area is what you're paying for in capital outlay. You have to buy a heat exchanger. You're paying for a larger heat exchanger so that you can have a smaller driving force and get the same heat flow. The second exchanger that we looked at had a larger driving force and requires less area, less metal, less cost. But it costs more to run because with that, the higher inefficiency, we had to produce air at 500 rather than air at 400, and that'll cost us more to do. As an engineering analysis, you want to look at the total cost. Here we have the operating cost, which deals with your efficiency. The larger the area, the smaller the gradient, the more efficient and the lower the operating cost. But the larger the area, the more metal we have in the exchanger and the higher the capital cost for that exchanger. When we put those two together and do an economic analysis, typically we'll have a curve that gives us a total cost that has some sort of minimum, and that minimum is how we optimize our exchanger area. We'll find the minimum that minimizes the total cost, and that's the area we'll use. Now let's talk about valves. Valves are irreversible also. Anytime you're using you have a gradient. Here it's a pressure gradient. It's going from a high pressure 5 atmospheres to low pressure 1 atmosphere. And in a valve we're getting nothing for it. You recall the energy balance on the valve gives us mass H1 equals mass out H2. Or if we treat it as an ideal gas, if it's an ideal gas going through the valve, such as air that we have here, then MCP T1 equals MCP T2, or T1 equals T2 for the ideal gas going through the valve. Now let's look at the entropy balance on that valve, and we'll use our equations that we have to calculate entropy change for an ideal gas. Here T1 equals T2, so this part, the left-hand part of this equation, drops out, and we have just simply minus R over molecular weight ln of P2 over P1, and notice that's log of a number less than 1 is negative, so a negative times a negative is a positive, and we have always a positive entropy generated. Irreversibility of that valve turns out to be 138.3 kilowatts. That's work that might have been captured had we let the gas do some work while it was expanding. So valves just pure friction. Nothing let's say productive happens in that valve other than dropping the pressure. Another irreversible process that we see a lot is mixing. Mixing is highly irreversible. Think of it this way. When I mix two things together, hot water and cold water, it's a lot harder to unmix than it is to mix. In fact, to unmix, I'd have to put some form of work in to make the process go backwards. So here we have the entropy generated is, well, we plug in the Here we just have liquid water, so we'll take the delta H for the water. If we put it in at 30 degrees and 50 degrees, it come out at 40 degrees. So we have out minus in for the cold water that went in. So that was 313 over 303. There's the entropy change of that. By the way, you could take the entropy for these streams from your steam tables, you know, approximating the enthalpy as, or the entropy as that of a saturated liquid. You'll come up with the same result. In fact, I recommend you do that. And then the entropy change for the 1 kilogram per second of hot water that came in is ln of T out, which 313 is 40 degrees C. We've got to put it in Kelvin, got to put it in absolute temperature. We come up with a positive entropy generated by mixing those two streams. So, entropy change of solids, we looked at delta S is equal to C, some CV, CP, ln of T2 over T1. We looked at irreversibility and how to calculate the irreversibility, and that's just a good measure of the inefficiency of a process in terms that we can understand work, and we can actually put a dollar figure on that, the work or the irreversibility, or the, let's call it the work lost, or the lost potential to do work. And that's a function of the gradients. The higher the gradient, the higher the irreversibility, the more inefficient the process will be. So for homework, what I'd like you to do is take those problems you've been working where you calculate entropy generated for heat exchangers, for valves, and mixing problems, and go back and just calculate the irreversibility. And when you can, like for instance for a heat exchanger, look at how much irreversibility that is compared to the heat that's flowing through there, and just kind of get a feel for the size of these numbers here.